This is a problem related to optics. So at this point, if you like, you can pause the video and try out the solutions by yourself, or else we can go ahead and start working on the question. So it says that the image on the retina of a human eye is a combined effect due to the aqueous humor and the eye lens. So it's talking about the human eye. The retina of a human eye is this part. It's at the back of the eye. That's what we call the retina. That's where the image is constructed. Then the aqueous humor is this part, and the eye lens is this one. It can be assumed that the aqueous humor is a convex lens with a fixed focal length. So we can assume that the aqueous humor can be modeled as a convex lens. So if you recall, convex lens is something like this. It is also called a converging lens. That's a convex lens. So the aqueous humor can be considered as a convex lens with a fixed focal length, and the eye lens can be considered as a convex lens with a variable focal length. So the eye lens can have variable focal length. That means its curvature can change. So this question, as I mentioned earlier, it talks about our human eye and how we can apply the knowledge of optics to delineate this problem. So the first part of the question talks about when viewing an object at infinity. So you place an object far away from the eye, practically it's at infinity. It is known that the optical power, usually optical power is denoted by an uppercase P, of the eye lens is plus 35D. This symbol D stands for the SI units of optical power, that is called diopters. Diopters are measured in meters. Actually, it's like 1 over meters, inverse meters. If that's the case, calculate the focal length of the aqueous humor. The distance between the retina and the eye lens is 2.5 centimeters. So that means this distance is given as 2.5 centimeters. That's 2.5 centimeters. Part B, when viewing an object 25 centimeters away from the eye, then determine the focal length of the eye lens. You will have a different focal length for the eye lens, because remember, the eye lens can be considered as a fixed focal length, a lens with a fixed focal length. So for each A and B, you are going to have two different focal lengths for the eye lens. However, the focal length of the aqueous humor is fixed in both cases. So now let's look at what are the required equations and other conventions that we need to solve this problem. When I say required equations and conventions, I mean related to optics. So the first thing that you will need is the thin lens equation. So thin lens equation can be stated like 1 over V plus 1 over U equals 1 over F. So if we represent a lens like this, its focal length is F, and then this line is a line that goes through the optic axis of the lens, and you place an object here denoted by O. The distance between the center of the lens and the object is what we call U, the object distance, the distance to the object from the center of the lens. And suppose that the image is constructed on the opposite side of the object. So that's the image. We call this distance, the distance between the image and the center of the lens, as V. So those are the terms. V stands for the image distance, U stands for the object distance, and F stands for the focal length of the lens. The lens could be a convex lens as shown here, or it could be a concave lens. Now the sign convention, that is also something important when we solve this problem. Sign convention for lenses, because we also talk about mirrors, but here we are looking at lenses. So again we can represent the lens as a convex lens, a converging lens. Let's say that the light comes from left to right. That's the incident light, and this is the refracted light. This is the direction of light. Now, if light goes from left to right, and suppose the object is on this side, then we consider the object distance to be positive. So in this case, U is considered to be positive. Suppose that the image is on the same side as the object. So I stands for the image, so let me write that. O stands for the object and I stands for the image. So if the object and the image is on the same side as the object when light is going from left to right as shown here, then the image distance here is considered as negative. Now let's look at the other side for the refracted light. For the refracted light, if the object is on that refracted light side, again light travels from left to right, then in this case the object distance is considered negative. However, the image distance, if the image is on this refracted light side where light goes from left to right, that's considered as a positive value. So image distance is positive, object distance is negative. So remember, light travels, light goes from, in these two cases, light goes from left to right, and that's also very important, the direction of the light. So that's the second idea that you need to know. The third one is the composite lens equation. Composite lens equation, or sometimes it's called the combined lens equation. So say that we have two lenses. It could be concave and convex, two concave lenses, two convex lenses. It could be any combination, but you have two lenses that are touching one another, that are in contact. That is all. That is very important. The two lenses are in contact, so they are touching one another. That is very important. So something like this. Let's consider two convex lenses. So that's one lens, and the other lens is touching the other one. So let's call this F1 and this is F2. We can combine these two lenses, and we can represent that by one lens we can call it the composite lens F. Its focal length is F. So there's a relationship between the individual focal lengths F1 and F2 and the focal length of the combined system. So this F stands for the focal length of the combined system, system. So that's given as 1 over f1 plus 1 over f2 equals 1 over f. So if it's a concave lens, you need to know that you have a negative sign, and if it's a convex lens, you have a positive sign. But that's the equation. So first we talked about this lens equation, or what we call the thin lens equation. Then we talked about this composite lens equation. That is also something important. And then another thing that talks in this problem is called the optical power. So optical power, usually it's denoted by an uppercase P, or optical power P is related to 1 over the focal length, and the focal length should be measured in meters. For this case, it should be measured in meters. If it's measured in meters, then the units of P is called diopters, measured in diopters, or in other words, inverse meters, diopters. So that's the connection between optical power and the focal length. If you have a lens with a certain focal length, convert that focal length to meters and take the reciprocal or inverse of that value, and you get the optical power. For a convex lens, the optical power is positive. For a concave lens, the optical power is negative. Keep that in mind. Now, the optical power of this composite lens system, so optical power, that's the final one we are going to talk before solving the problem. Optical power for the composite lens system that is this one. You have two lenses together like that. One is f1 and the other one is f2. In this case, the combined or the composite lens, combined lens, if we call it f, then what is the relationship of the optical power? So here, let's say optical power is P, here it's P1 and P2. In terms of optical power, it's simply the sum of the individual optical powers, P1 plus P2. So these are the important things that you need to know before solving this problem. Optical power for the composite lens, then composite lens equation, sign convention for lenses, thin lens equation. So again, let's go back to the first part of this question. When viewing an object at infinity, it is known that the optical power of the eye lens is 35 diopters, positive 35 diopters. Calculate the focal length of the aqueous humor. The distance between the retina and the eye lens is given as 2.5. So here, so in part A, it says that the object is at infinity. So light rays coming from infinity can be modeled as rays that are parallel. So this is part A. So it talks about light coming from infinity, since the object is at infinity. Now light coming from infinity can be considered as parallel rays like this. So light comes like this, and then it falls on the aqueous humor lens system. So this is the lens system in our problem. And then what's going to happen is that this, in order to see the object, so I'm showing you the cross section of the eye, what will happen is that this light will refract and they will fall to the retina. Otherwise we won't be able to see that object. So they are going to fall exactly right on the retina. Then we say we can see that the image of that object. So that means this distance, since this distance is given as 2.5 centimeters, that's going to be the focal length of the composite lens system. Since light from infinity falls on the retina, we can say that the focal length of the system is equal to plus 2.5 centimeters. So this is the focal length of the system. And when we call the system, that is the aqueous humor plus the eye lens, that's our system. Okay, so we can obtain from here, what we can do is that we can obtain the optical power of the lens system. So that means D is given by 1 over the focal length of the system, and this would be 1 over 2.5 times 10 to the power negative 2, because 2.5 is centimeters. In order to get a diopter value, I have to convert that into meters. So 1 over 2.5 times 10 to the power negative 2. And if you solve this, you are going to get plus 40 diopters. Now we recall that the optical power of the system is the sum of the individual optical powers. So D1 and D2 are the optical power of the aqueous humor plus the optical power of the lens. Now for the eye lens, it's given that D1 is equal to plus 35D. So we can substitute D1 here. Since we know D, we can find the focal length of the aqueous humor. So that would be plus 40D is equal to plus 35D plus D2, and here we get D2 is equal to plus 5D. So from this one we can find what is the focal length of the aqueous humor, that is F2 is equal to 1 over D2, and this is 1 over 5, so that is 0.2 meters, or in other words that is plus 20 centimeters. So that's the answer for the first part. The focal length of the aqueous humor is plus 20 centimeters. Now let's look at part B. In part B, the light does not come from infinity because the object is now 25 centimeters away from the eye lens or this lens system. So it's something like this. That's your eye, and then this is the point where the object is. Now this distance is 25 centimeters away from the lens system. Still the distance between the eye lens and the retina is 2.5 centimeters. So light falls like that onto the retina, and then we can see the image of that object. So here you have to remember that this is still the lens system. Now in this case, we can use the lens equation, the thin lens equation, 1 over V plus 1 over U equals 1 over F to figure out the focal length of the entire system, the lens system. 1 over V, you can see V is considered the image distance. The image distance, it's to the right of the lens, so that's a positive value, plus 2.5 centimeters. You can see the object distance, where the object is to the left of the image. For the left of the, you can see the object is to the left of the lens, and that is again considered positive according to the sign convention. So we have plus 25, and then that is equal to 1 over F, where F is the focal length of the entire system. Now if you consider the focal length of the entire system here, in this case you are going to get F as equal to 2.27 centimeters. 2.27 centimeters. That's the focal length of the system. Focal length of the lens system. Now remember, in part A, the focal length of the system was plus 2.5 centimeters. But now in this case, the focal length of the system is plus 2.27 centimeters. The reason for that is, look at the object distance. In part A, the object was at infinity. In part B, the object is now 25 centimeters away from the lens system. So something has to change in terms of curvature, and the only thing that can change is the eye lens. The lens curvature can change, but as mentioned earlier in this problem, the aqueous humor is considered as a fixed focal length. Now, in order to find the focal length of the eye lens for part B, I'm going to use the composite lens equation. So that means from 1 over F equals 1 over F1 plus 1 over F2, I can solve for F1 in this particular case. So you have 1 over F is equal to 1 over plus 2.27 centimeters, and then 1 over F1, that is what we need to figure out. 1 over F2 is 20 centimeters, so I'm going to substitute 20 over there, because that's the focal length of the aqueous humor. And then we can solve for F1, and you will see that F1 is equal to plus 2.56 centimeters. So that's the focal length of the eye lens for this second situation. Now if you consider the focal length of the eye lens for the first situation, that means when the object was placed at infinity, that was 2.85 centimeters or 2.86 centimeters up to 3 sig figs, because from here you can figure out that F1 1 over 35, and you have to convert that into centimeters. So if you do that, you'll get plus 2.86 centimeters. So you can see the focal length for the eye lens in part 1 is greater than the focal length for the eye lens in part 2. The reason for that is now the curvature of the eye lens has increased. When the curvature increases, the focal length reduces.